Welcome to the deep dive, and a special welcome to our CSWIP 3.1 exam prep series.
Great to be here.
Yeah, so if you're getting ready for that CSWIP 3.1 Welding Inspector Exam, well, you're definitely in the right place.
Absolutely.
Our goal in these sessions, it's pretty straightforward. Help you sharpen up on those critical concepts, maybe spark a few aha moments, and really give you the solid knowledge you need, not just to pass the exam, but to be effective out there.
Right. It's more than just the answers.
Exactly. So today we're going to tackle some multiple choice questions, the kind you'll likely see. We'll break them down.
Yeah, and it's really not just about spotting the right option. It's understanding why it's right. Those underlying principles. That's what makes a good inspector.
Totally agree. Understanding the why is key.
Knowing that helps you understand issues, maybe even prevent them before they happen. So yeah, let's get into the logic.
Perfect. So let's test your knowledge. First question up. Question 1. EN 2560. Standard refers to which of the following? Okay, your options are A, welding terms and symbols, B, covered electrodes for MMA, C, filler wires for MIG-MAG and TIG, or D, saw flux. Have a quick think. Which one is it?
Okay, so the correct answer there is going to be B, covered electrodes for MMA, manual metal arc welding.
MMA electrode.
Yeah. EN 2560, that's a European standard, and it's specifically for classifying those types of covered electrodes. It covers, chemical composition, mechanical properties of the weld metal, how they run, the whole package, really. It's all about making sure they meet the quality and performance needs.
Okay, so it's very specific then. But I mean, beyond just the exam, what's like a real world situation? Where would mixing up EN 2560 with, say, a TIG standard actually cause a problem on a job, a serious one?
Oh, that's a really important point. Huge implications. Imagine, you've got a WPS, a welding procedure specification, and it specifies an electrode under EN 2560, maybe like an 42.3B, 32H5, something specific.
Gotcha.
Now, if someone, maybe the inspector, maybe the fabricator, they grab the wrong standard. Maybe they look at EN ISO 14341, which is for MIG wire.
Yeah.
They could easily end up ordering or using the completely wrong consumable. And that small mistake, it could mean the weld metal just doesn't have the right strength or the right toughness. Maybe the hydrogen level is wrong. And the result could be anything from failing compliance checks, needing costly rework, project delays, or worst case, a failure later on. It shows you just have to be precise with these standards. It's not optional for an inspector.
Wow, yeah. That really brings it home. It's not just ticking a box. It's fundamental to getting the right material and ensuring the weld holds up. Okay, let's switch gears a bit from standards to a really practical issue with consumables. Question 2 is, which type of submerged arc welding flux is susceptible to moisture pickup? Options.
Yeah.
A, neutral. B, agglomerated. C, fused. D, all about the same. Think about how they're made.
Right. The one you're looking for here is B, agglomerated flux.
Agglomerated. Why is that?
Well, it's down to how they make them. Agglomerated fluxes, they mix raw materials with a binder, make pellets, and then bake them, but at fairly low temperatures.
Okay.
And this process leaves them with a kind of porous, granular structure. Think tiny little sponges.
Wow.
So because they're porous, they're really hygroscopic. They just soak up moisture from the air if you're not careful with storage and handling.
Unlike fused flux.
Exactly. Fused fluxes are different. They melt all the ingredients at really high temps, then crush the glassy stuff that results. It's dense, non-porous, much less likely to grab moisture.
Right. Okay. So let's say that agglomerated flux does get damp. What actually happens in the weld? What are the real dangers? And maybe more practically, what makes keeping it dry so tough on a busy site?
Oh, the consequences are serious.
Yeah.
Very serious. If moisture gets into the weld pool from the flux, the heat breaks it down into hydrogen.
Hydrogen.
And that hydrogen dissolves into the molten metal. When it cools, the hydrogen gets trapped. That can cause hydrogen-induced cracking, sometimes called delayed cracking, because it can show up hours, even days later.
Wow.
Plus, it massively increases the risk of porosity, little gas bubbles in the weld.
Not good.
Definitely not good. And site challenges, plenty of those. Storage might be poor, maybe high humidity, maybe the redrying ovens aren't working right, or people just leave bags open.
Yeah, I can see that.
An inspector has to be constantly checking storage areas, oven temps, making sure flux is issued properly, not left lying around. It's a real battle to keep that moisture out and ensure quality.
That really highlights how prep is just as vital as the welding itself. Knowing about that manufacturing difference, that vulnerability, that's key to stopping defects before they start. Okay, so we've talked prevention, but what about finding defects? That brings us to NDT. Question 3. When considering radiography using X-ray, which of the following techniques is most likely to be used for a pipe-to-pipe weld? Circumferential seam, 610 millimeter diameter with no internal access. Options again: A, SWSI, B, DWFSI, C, DWDI, D, SWSI panoramic. Look at the constraints. Circumferential seam, big pipe, 610 millimeter, and crucially, no way to get inside.
Right, those constraints are absolutely key here. Given a large diameter pipe like 610 millimeters and no internal access, the technique you'd most likely use is B, DWSI, double wall, single image.
DWSI. Okay, why that one specifically?
Well, think about it. With DWSI, you put the X-ray source on the outside of the pipe, and the film goes on the opposite side, also on the outside.
Okay.
The radiation goes through both pipe walls, top and bottom, but, and this is the clever bit, only the image of the weld nearest the film gets recorded clearly enough to interpret properly.
For a full circumference on a big pipe, you'd just move the source and film around, taking multiple shots to cover the whole weld. It neatly gets around that no internal access problem.
Okay, that makes sense. But why not the others? Like, why wouldn't SWSI or DWDI work here? It's not just pick one and go, is it?
Definitely not. It's all about picking the right tool for the job, based on the situation. So SWSI, single wall, single image, that usually gives the best image quality.
Right.
But for that, you normally put the source inside the pipe, aiming out at the film on the outside. Great if you can get inside, but with no internal access on a 610 millimeter pipe, impossible.
Okay, so SWSI is out. What about DWDI?
DWDI, double wall, double image. That's really for much smaller pipes, maybe up to about, say, 90 or 100 millimeters.
100 kilometer diameter.
Yeah. With DWDI, the radiation goes through both walls, and you actually see two images of the weld, one laid over the other on the film. It can be tricky to interpret, and it's just not practical for inspecting the entire weld on a large pipe like this.
And the panoramic one. SWSI panoramic. Fantastic technique for circumferential welds. Gets the whole thing in one shot sometimes. Uses a special source inside the pipe that radiates outwards 360 degrees to film wrapped around the outside. But again, it needs internal access to place that source. No access, no panoramic. So DWSI becomes the logical, practical choice for this scenario.
That really shows a problem-solving side of inspection, doesn't it? You're not just following a procedure. You're figuring out the best way to apply the right technique, given the real-world limitations. That needs proper understanding. Okay, let's shift to mechanical testing. Question 4 digs into what happens when materials fail. In a transverse tensile test, brittleness would be indicated if your options. A, there is a reduction in cross-section at the position of fracture. B, the fracture surface is flat and featureless but has a rough surface. C, fracture occurred in the weld metal. D, the fracture face shows beach marks. Picture holding that broken piece. What tells you it was brittle?
Right. The key indicator for brittleness here is option B. The fracture surface is flat and featureless but has a rough surface.
Flat and featureless but rough. How does that work?
Okay, so when something breaks brittly, it fails suddenly with very little or basically no plastic stretching or deformation beforehand.
Just snaps.
Pretty much. Visually, that means the break surface looks flat. You don't see that necking down, that reduction in area you get with a ductile material stretching before it breaks.
Yeah, right.
The featureless part means you don't see things like shear lips or a cup and cone shape. But rough means kind of microscopically the surface has this crystalline or granular texture because the crack just rips through the grains quickly. Cleavage fracture.
Gotcha. So how does that stand out from the other options? Especially A, the reduction in cross-section. And if an inspector saw that brittle fracture in the field, what should happen next? What's the thought process?
Well, option A, that reduction in cross-section, maybe with a cup and cone look, that's the classic sign of a ductile fracture. The material stretched, absorbed energy, then failed. So A is the opposite of brittle. Option C, fracture in the weld metal, just tells you where it broke, not how. Welds can break brittly or ductily.
Right. Location isn't mode.
Exactly. And D, beach marks. Those are telltale signs of fatigue failure. That's from repeated loading over time, a totally different mechanism. It doesn't tell you about the material's basic brittleness in a single pull test. Now, if you see that flat, rough break in the real world, alarm bells should ring.
Okay.
The immediate investigation would be, first, material confirmation. Was the right stuff used? Check the certs, traceability. Then review the welding procedure critically, things like preheat, inner pass temp, any post-weld heat treatment, because those control the microstructure and can prevent or cause brittleness. And you'd also look at service conditions. Was there some unexpected stress or maybe a very low temperature involved? That visual clue, that flat, rough surface, it's a massive pointer towards why something failed.
It really is like materials forensics, isn't it? Reading the story told by the fracture itself. That's a vital skill. Okay, last question for this session. This one brings together material science and welding parameters. Question 5. Which of the following test pieces taken from a Charpy test on a carbon-manganese steel weld, welded with a high heat input, is most likely to have the lowest toughness? Options: A, parent metal, B, weld metal, C, HAZD. All the same. Key things: high heat input and carbon-manganese steel.
Okay, this is a really important one in practice. The area most likely to suffer to have the lowest toughness in this situation is C, test piece taken from the HAZ, the heat-affected zone.
The HAZ. Why specifically the HAZ with high heat input?
Well, when you weld carbon manganese steel using high heat input, you're pumping a lot of energy in over a longer time. This means the HAZ, the metal right next to the weld, gets very hot for quite a while, and then it cools down relatively slowly.
Right, slow cooling.
And that specific thermal cycle, especially in CMN steels, causes the grains in the metal structure to grow quite large. We call it the coarse grain heat affected zone, or CGHAZ.
Big grains are bad for toughness.
Generally, yes, especially in these steels. That grain coarsening, plus the slower cooling, can also lead to some undesirable microstructures, forming things like Widmanstetten ferrate or coarse pearlite. These structures are just inherently less tough, more brittle, especially when it gets cold or if it takes a sudden knock.
I see.
The parent metal, away from the weld, it keeps its original properties, more or less. And the weld metal itself, if the procedure and consumables are right, might be okay. But that HAZ is often the weakest link toughness-wise when you use high heat input. That's why controlling heat input is so critical.
That's fascinating. So the act of welding itself fundamentally changes the material right next to it, and not always for the better if you're not careful. What does that mean when an inspector looks at a WPS, and how does it affect thinking about the structure long term?
It means an inspector needs to look really closely at the heat input limits specified in the WPS, particularly for materials like CMN steels. If the procedure allows for really high heat input, or if they see evidence that a welder has exceeded it, maybe wide weld beads, slow travel speed red flags should go up.
Okay.
They should anticipate a potential drop in HAZ toughness. Maybe they'd recommend extra testing, like more Charpy tests focusing on the HAZ, long term. A low-toughness HAZ is basically a built-in weak spot. It's where a crack is more likely to start if the structure sees impact loads, operates at low temperatures, or even if small defects are present. It's a direct link between understanding microstructure and predicting real-world safety and performance.
That really sums up the inspector's vital role, connecting the science to the structure safety. Understanding those changes is where this deep knowledge really counts. And just like that, we've worked through 5 pretty important questions for your CSWIP 3.1 prep. We had standards, consumables, NDT methods, and how materials behave under stress and heat.
Yeah, quite a range.
The idea really was to get you thinking beyond just the multiple choice answer. So definitely go back over these concepts. Think about the why we discussed for each one. That's where the real learning happens.
Absolutely. Like we said at the start, it's the understanding, not just memorizing, that makes the difference, that knowledge sticks with you long after the exam. And maybe as you keep studying, think about this. We focused on how heat input affects toughness, but how might it affect other things, like hardness or corrosion resistance, or even the stresses left in the weld? And what would that mean for different jobs the weld might have to do?
Ooh, that's a great question to chew on, connecting all those different properties together. Excellent thought. Well, thank you so much for joining us on this deep dive.
My pleasure.
We hope it was useful for your prep, and we'll look forward to seeing you back here for the next session in our CSWIP 3.1 exam prep series. Keep learning, keep questioning, and we'll talk soon.